Welcome to a lesson with Dr. Powell. Let's take a look at some properties of an operation which we can perform in matrices called taking a transpose. We notate it this way with an A and a capital T above it. Notice that when we take the first row and it becomes the first column. Second row becomes the second column. Third row becomes the third column. First column becomes the first row. Second column becomes the second row. The rows and columns switch places. This is how we get the transpose, called a transpose, of a matrix A. Now, what does it mean? What is its usefulness? Let's look at the matrix A and consider it as under a column interpretation when we multiply. Let's just remind ourselves what this is. The domain is R2 and the codomain is R3. This is because this matrix describes where E1 is going to travel, and it describes where E2 is going to travel. And so that comes from R2. So when we input a vector, it's over here, say like 1, 2, we input it, and the output would be 1 times this column plus 2 times that column. Okay, so that's a column interpretation. Now, there's an equivalent row interpretation for matrix multiplication. So where we input something on the left here as a row, such as maybe like 1, 0, 1 inputs, and then it outputs, because what we're doing is we're adding rows together. So 1 times the first row plus 0 times the second row plus 1 times the last row. And so doing so, we're just, in this particular case, we would get 3, 1. So that's a row interpretation of this as a function, this matrix as a function. Okay, so we have 2 different interpretations for matrix multiplication for the same matrix. Thinking of it as a function, either we can take vectors on the right as columns or vectors on the left as rows. Now, what if we want to stick to just one interpretation, say like column interpretation? Then the matrix that would describe the linear transformation that we have in the row interpretation, where we're like inputting R3 and we're outputting R2, but we want to represent this in a column interpretation manner. That is the transpose. Let's see that let's see that in action. Okay, so here, let's think of a column interpretation, and let's input 1, 0, 1 like we did before. Now we say 1 times that column plus 0 times that column plus 1 times that column, and the result would be, in this case, 3, 1, which is exactly what we had over here, but it was as a row. So what we see is the linear transformation that A described in its row interpretation is now the column interpretation of A transpose. Okay, the column interpretation of A transpose was the row interpretation of this guy. Now, actually, if you take the row interpretation of A transpose, you actually get the column interpretation of A, so it works back and forth in that way. It's kind of a fun setup, but it's just a way, if you want to stick with one interpretation, then but you want to be able to describe the transformation that the row interpretation would give, then we just use the transpose. So let's take a look right here. So let's suppose we have the product AB, and we take its transpose. Well, that means that we're considering a matrix whose column interpretation is the same as AB's row interpretation. So A times B as a row interpretation would be like you input this way, and then you output because it's a sum of rows. Okay, so the number of rows represents what you're like the different standard basis that you're inputting, which should give you the dimension here into A. So if, like for instance, in this case, you'd be inputting R3, be outputting R2. Now R2 would then come out and be the codomain, and that codomain would come into the domain of B, and then you output like that. So kind of in this type of schematic here, using a row interpretation of A, using a row interpretation of B in sequence. And that's what the row interpretation of AB is. Now let's think about that in terms of columns. So to get this row interpretation, we would do this with A transpose. And then to do this, we would do this with B transpose. Notice that naturally it looks like with column interpretation, we'd first be multiplying over here on the right in our function. This would be A transpose and then B transpose. So matrix multiplication is discomposition. And with column interpretation, the composition goes the way it usually goes. So input to output going from right to left. And so naturally, AB transpose is actually B transpose A transpose. Notice it's in the opposite order. Now, if you take A plus B, so you add the entries in the matrices before you switch columns and rows, it should be the same thing as switching columns and rows individually and then adding. It takes the individual places to the same things to the same places. So matrices are functions, and they add just as functions add. You just add their outputs together, and in particular, the columns or the rows, depending on your interpretation, actually give you outputs of specific vectors. And so if we add those together, we're actually adding outputs of things similar to the idea, like if you have like f of x equal to x plus 1 and g of x is equal to x squared, the f plus g function is just x squared plus x plus 1. You just add them together. So matrices really kind of follow the same idea. If you think of them as functions, you're just adding outputs together and defining what it was as a function. All right, let's come over here. All right, let's come over here to, so over here, we have a matrix M, and suppose we put it in Smith normal form like this, and it's surjective. Notice its transpose is like this, and this represents something that's injective. Surjective, since its codomain is in the column interpretation is R2, and we have the dimension of the range is the same as the number of ones we have here. Now here, this is injective because there are no columns of zeros. So, and so we notice that when you take a transpose of a matrix, it actually changes from being surjective to injective, or vice versa if it was surjective to begin with. So that's something that happens with transposes. So what do transposes do? Notice that transposes actually switch a domain and codomain. They switch those. They also switch properties such as surjectivity to injectivity, or injectivity back to surjectivity. That's one thing that they do. All right, let's take a look at a little thought exercise. Vectors, we can think of them as columns or rows. Now, thought of as a matrix, a column is like you input R and you output R2. So you could think of a vector as being a function as a matrix. You could also think of a row vector as being a function from R2 to R. So it kind of makes sense. I mean, E1 is going to go to the first entry, E2 will go to the second entry. Or here, the number 1 actually goes to the vector itself. So you can think about vectors in these ways. Sometimes this is called a dual vector, if you will, in this type of interpretation. But it's interesting to kind of think about how this works with transposes using this property. So if you have like A of V instead of A times V, especially if you're thinking of V as a function, notice what this does. So what does V do? V goes from R to R2, and then A takes R2 and puts it to R3. So the combined composition is going from R to R3, so you should expect a R to R3, a column with 3 things in it, which is exactly what we would expect if we put so if we put 1, 2 into A, we'd get out 1, 2, 4. Okay, now if we take transposes, see what that does. A transpose goes from R3 to R2, and VT goes from R2 to R. So cumulatively, we get a function that goes from R3 to R, which is the row 1, 2, 4. So we could think about matrix multiplication even just as function composition, if we will, if we wanted to, as like a combined composition map. Just another way of thinking about it. Now, here's just another thought. What if we think of a row interpretation of A transpose? Now, naturally, the row interpretation of A transpose should actually get us to the column interpretation of A. So the row interpretation, we put a row in here, and we have 2 rows here, so we put a row of size 2. Hey, that's like putting a column of size 2 right here with A. So we could think of it going that way as well, such as like, so we input VT because it's a row, right? And we output like a WT or something like that. That would definitely work. We could do something like that. But really, that's just another funny picture of just using A itself. So we get these kind of different schematics, different properties with transposes. Basically, what you can remember is they reverse the order of multiplication. They give you something, a way of describing the row interpretation of A as a column interpretation. And they switch like surjectivity, injectivity type properties. Thanks for watching.